start. Okay. So today we're going to talk about some notes, and I'm going to call these notes density. So making sure I'm not forgetting something here. Whenever we talk about density, there's just a couple of things that we always measure. We measure mass. What unit of measure do we use to measure mass? Grams. And what unit of measure do we use to measure volume? We can use milliliters. The milliliters is kind of the most common, especially like in this class, just because we deal with small amounts of things. But of course, you could do liters. We also could do another one that we'll see a lot is called cc, or sometimes you'll see it written. I don't want to put a slash there. I want a comma. We'll see it written this way. Anybody know what that stands for? Cubic centimeters. So that's why it's cc, or cubic centimeters because it's centimeters cubed. So same thing. But the important thing is that all of these units of measure are actually the same exact amount. They're actually in the metric system of measuring. They actually defined some of these based. I'm forgetting right now which way it went. I think they defined. Yeah, they took the centimeter and they made it cubed and called it a milliliter. They actually did it with the liters first, but you get the idea. It's like, we use both. You mean both of these here, or like all three? I'm saying we use them all just because they. I don't. That's a good question. I mean, like I've seen syringes that say cc. I've also seen syringes that say milliliter. I don't know why exactly. I would imagine there are certain situations where one is more useful than the other. I don't know, but that it doesn't matter. The point is, it doesn't matter. So that's what we do there. Okay. Density is what we get when we take mass and divide it by the volume. You could also think about it as being this. How much matter? What's matter?
Space, or like
Stuff. A very excellent but non-scientific definition for matter is just simply stuff. Is in how much space. Am I writing clearly and big enough for you?
Yeah.
And then just to kind of emphasize this, how these two things are really the same. You see how that color coding kind of helps you see that that's really the same thing? Because mass is how much matter, and volume is how much space. Right? So therefore, when we measure density, we end up measuring it with these units of measure. What's on the top? Grams. What's on the bottom? Milliliters. Or therefore, it's the same as... Oh, I'm sorry. Or sometimes we would write it, right? Can you see that all these things are really just the same thing?
Yeah.
All the same thing. Coincidentally, if we were going to take a long dig into the metric system, then I would work this out for you, but I'm not going to worry about that. I'm just going to give it to you one time. There's one other one that you might see sometimes, which is, what's that stand for? Kilograms, which is 1,000 times bigger than a gram, right?
Yeah.
What's L?
Liters.
How much bigger is a liter than a milliliter? 1,000 times. So can you see that that's also the same thing?
Yeah.
But just if you see that now, you know it's the same thing. Okay? All right. So now I need somebody to pull out one of their data points from the lab. Who's got a data point handy from the lab?
What?
Turn over. In fact, I want you to do this. Everybody should do this. I'll write one up here, but you should do this with one of your data points. I want you to find a data point from your lab that's like, pick your favorite one in the next 2 seconds. Doesn't matter which one. And we're going to calculate the density of water. Are you ready?
Yeah.
Can you do it? I bet you can do it. Can you find the gram number and divide it by the milliliter number? Sure, you can use a calculator. You might not really need to.
What do we divide with?
So you put the mass on the top, the grams on the top, and the volume, the milliliters, on the bottom, and just divide it. So like this. Who's got one real handy for me? Give me one, Julia.
So ours was 1.5 milliliters equals 1.71 grams, and so the density would be 1.14.
So 1.71 grams divided by, I'm running out of room on the paper here, but that's okay. 1.5 milliliters equals, what was the number exactly? 1 point what?
1.14.
Okay. So just a little heads up of a warning to you here. As we move forward here, we're going to do some practice problems where you calculate the density of this stuff. And this right here in my little squiggly non-boxy thing is the amount of work that I want you to show for me when we set up these problems and I grade them on a quiz. Does that sound good? So always show the first measurement with its unit of measure and the other measurement with its unit of measure and show them being divided, and then show the ending answer with its unit of measure, which notice that it has 2 for units of measure. All right? Next thing I want you to look at the graph that you made in your book the other day. So this was, I just did this when somebody, Julia shared the data with me for this exact measurement. You all found something, I'm guessing, close to this number. Is that accurate? Not precisely the same, but if we were to average them together, we'd come up with something close to that.
Yeah.
Is that right?
Ours is like 0.9.
Yours is 29?
0.9.
Oh, it's 0.9? Like 0.9? Oh, yeah, that's fine. That's fine. Because think about it this way, guys. What is your level of confidence in getting that syringe to stop at the precisely exact spot?
At least 100 out of 100.
Like if you were to move it, like, I can't even move my fingers that small amount, but like if you were to move it like just a teensy weensy bit wrong, can you see that it squirts some of the water out and therefore makes a different measurement?
Yeah.
Right? So like this is not a perfect system, right? It's pretty good. It's reasonably good. But yeah, if we're off a little bit, that's okay. So what I want you to look at is I want you to kind of do a rough estimate on your graph and see, can you tell me what is the slope of that line roundabout? So just quiet and think about it for a second. What is the slope of that line? Look at your graph, see if you can figure it out. It goes over what and up what?
Oh, I put more graph.
Well, but you can still look at the top of your bars.
Oh. It's like, oh yeah, you're right. Well, mine's different.
Yours is different?
Mine's like 4. Mine's like just 4, but just like I did like mine spread out. On the graph, like I went by like 4s.
Well, but then that's okay because your 1 is still also spread out.
Yeah. What?
So I'm not talking about how many blue boxes of the graph paper it goes over and up. I'm talking about how many units of a whole numbers it goes up. Does that make sense?
Yeah.
So the fact that you spread it out on your graph doesn't change the answer.
Yeah. I'm like not in it. I'm too tired.
You're what?
I'm too tired.
Well, that's okay. It's Friday, right?
Yeah.
Did you find it? Did you get an estimate? Does it go over about 1 and also up about 1?
Yeah.
If you're having a hard time counting, look toward the end of your line and see if it helps you to kind of like think about it from the end. Sometimes it's kind of confusing if you look at like the ones that are super close to the origin. Oh, you didn't put them in order. Okay, so yours is kind of goofy. All right. What else?
Ours went over by like 0.5 each time.
Ah, that's interesting.
Well, we had a small syringe that would fit like 5. We did it in my house.
Oh, okay. So, what you should see on your graph, okay, is that if this is 0 and then mass goes up, right? Okay. What you should see is that it goes up 1, if this is 1. It'll also go over about 1. Okay? And if it goes up 2, it should also go over 2. And 3 and 3. So you should end up with a line something like this. And the graphs that I saw as you guys were making them, that's what they looked like. So that's good. I think they were good for the most part. They might be off by just a little bit, but in general, the amount that it goes up, it also goes over. Does anybody know how they come up with the definition of a gram? You know?
Oh, yeah, they like made it so if water would specifically be one, the whole system is based around that.
Right. They actually took 1 milliliter of water, and they took a 1 milliliter of water because they took, what is this? A ruler. This is actually a meter stick, but yeah, they took this and they took the 1 centimeter of water, 1 centimeter times 1 centimeter times 1 centimeter, that size cube, and they filled it up with water and they weighed it and they said, this is a gram. That's actually how they decided.
That's crazy.
I'm sure they talked about it a little bit more, but that's what the definition came up to be. They probably argued over it for months. What?
So how'd they figure out what was like 1 foot, like 12 inches?
That's like
Somebody measured their foot and decided that that's how long it should be because everybody's foot is the same size.
Yeah, I don't think that's a true story. I mean, they measured their feet to measure.
I mean,
but that's
yeah, in other words,
how
the
they
English
do it.
system is not the same. It doesn't work the same way.
Also, that's the imperial system versus, metric system.
Okay. All right. So, now here's the next question I have for you. What if we measured some different things that were not water?
What if it was?
Could we find the density of some things that are not water?
Yeah, like milk.
Do you got some milk? I don't have any. You got some?
Milk. We measure.
I've got a bunch of random stuff that we can measure.
Can we do that?
I do.
We can melt some Jolly Ranchers.
Melt some
Like
Jolly
Jolly
Ranchers.
Ranchers.
You can probably do it without melting them, actually.
Oh, you want to borrow some Jolly Ranchers?
I don't really want to borrow Jolly Ranchers, but I might let you do one. Okay, so here's what we're going to do. We're going to measure the mass and the volume of a bunch of objects and make a graph like this, but we'll make a bigger one that has more different kinds of objects on it. Okay? And we'll see how this all compares to water. Cool?
Yeah.
All right.